All right, welcome everybody. I'm really happy today to be presenting part two of this climate training with ARSET. This is a presentation focused on climate change, future scenarios, impact forecasting, and adaptation. My name is Alex Ruane. I am a research scientist at the NASA Goddard Institute for Space Studies, and I put this together along with colleagues, especially Dan Bader at NASA GISS. So let's jump in. So as I mentioned, this is part two of a two-part climate training by ARSET. Part one focused on climate change monitoring and impacts using remote sensing and modeled data. That was recorded and presented on September 29th. And this presentation will be given twice today, October 6th, and there will be follow-up in the weeks ahead. So in particular, if you are looking for a certificate of completion in terms of taking this ARSET training, there is one homework assignment. Answers must be submitted via a Google form accessed via the ARSET website. This homework is now available, and the due date is 2 weeks from today, October 20th. And if that is completed to satisfaction, then there will be a certificate of completion awarded to those who attend the live webinars, complete the homework assignment by the deadline, and then that certificate would come approximately 2 months after the completion of the course. The goals for this ARSET training really are oriented around how we can make climate information useful. That means we have to begin with the basics of climate information to make sure that those providing and using climate information understand the core processes involved. The use of climate models and how we can use them to project and understand the climate system. Historical versus future climate conditions. And approaches that we use to assess climate impacts. This helps us design climate adaptations and in that sense make use of this climate information. Okay, so let's jump in and begin with the climate change basics. I'm going to try to be very light in this presentation in terms of equations and technical details. So here I'm going to give just a very brief introduction in terms of the core radiative basis of climate change. The first fundamental process that is important to understand is that objects with warmer temperature radiate away more energy. So warmer temperatures means more energy is radiated away. So consider just a simple setup here where we have the moon and the earth and the sun off far in the distance. This is not to scale, of course. What's important to note is the moon has virtually no atmosphere. So in this situation, we have energy coming in from the sun, and it reaches these objects, and these objects are going to have an energy balance, which means the amount of energy coming in has to be balanced by the amount of energy coming out. And the amount of energy going out is determined by that temperature. So at this balance of energy, we have a temperature. Now, of course, the Earth is not like the moon in the sense that we do have an atmosphere. So when we add an atmosphere to this equation, or when we thicken the atmosphere with greenhouse gases, the same amount of sunlight is coming in, but some of the outgoing energy is trapped and directed back down towards the planet. This means in this situation, there's more energy coming in than the energy going out, which means the planet has to warm at the surface to get back into balance. That means we can re-achieve this energy in equals energy out, this climate equilibrium, but to do so, it has to be warmer. So overall, this greenhouse gas effect is the atmosphere trapping some of this energy and forcing this adjustment towards warmer temperatures. The current climate research and our efforts on applications are trying to take this fundamental radiative basis of climate change and extend them to understand what happens to that extra energy. Where does that energy go in terms of within the atmosphere, within the oceans, within ice, land surface, and vegetation? All of these components of the climate system could potentially take some energy. That energy changes the way that the climate behaves in terms of shifting atmospheric patterns, in terms of temperature and rainfall, for example, and winds. It changes the way we have extreme events. It changes the levels of the sea, And there are several feedback loops in terms of complex responses to these energy changes that can in turn increase or decrease the overall rate of energy exchange. This changing climate in turn affects nature and society and things that we care about. Of course, this begins with ecosystems and species, but also many human systems like agriculture, water resources, infrastructure, health, forests, fisheries, and transportation, and many more. Of course, the other big area of research and applications right now is understanding how our actions shape the future. That means we need to understand how the choices we make in terms of emissions, adaptation, and risk management will change the type of climate that we have in the future and our ability to be resilient to climate changes and respond to the climate as it shifts with us. It's important to take one step back here and think about the application that we're addressing and make sure that we're picking our models and data sets for the purpose of our application. And in that sense, it's worth going back to another fundamental, which is reminding ourselves that weather and climate have fundamental differences. What you see on the screen right now is a snapshot from Tuesday, September 21st, so just a couple weeks back, where this is the 2 meters, so the surface temperature, and we're looking at the difference between that day in 2021 and the average from a period at the end of the 20th century, from 1979 to 2000. And in that sense, where you see oranges on the screen are places that were warmer than the average September 21st, and where you see blue are places that are cooler than the average September 21st in that 20-year period. And what you'll notice on this map is that there are lots of interesting features and regional patterns, small scale, large scale, and a bunch of things to look at. A lot of this you might classify as the weather of that day, but there are also broader patterns to look at. One might squint their eyes and try to get an idea of what the global anomaly looks like, and you might see that there's a little bit more orange than blue, but you don't have to take our word for it. In the bottom left, you'll see that the world anomaly is 0.2 degrees Celsius warmer than that end of century period. That would be a climatological feature in terms of understanding that longer term, that statistical characteristic of the climate system, and understanding how that is evolving over the longer term. But it is worth noting that these weather patterns are often what people experience. And the statistical representation of weather patterns and the events and averages and extremes that are within that tell us about the climate system and how we can go forward. Now, it's also important to recognize, especially in this Northern Hemisphere fall season and Southern Hemisphere spring season, that there are many transitions, and it's often difficult, I have found, for people to remember what September 21st should feel like. It's difficult for us to know if today is a really hot day or a cool day, or maybe just an average day in these transitional seasons. So I personally enjoy this Climate Reanalyzer website where I got this map because it gives us an idea. For example, I'm sitting in New York, and this was a fairly typical September 21st day, even as our neighbors north in Canada were having a quite warm September 21st. Of course, when we look at these longer term climate trends, we see patterns that show the climate change that we're here to discuss today. On the screen now is the NASA GISS surface temperature analysis, which has been calculating anomalies of surface temperature at meteorological stations all around the world. On the left, you see the time series increasing as we come towards present. And here is just August 2021, showing that there have been warmer conditions across much of the world compared to the 1951 to 1980 period. This product is updated around the middle of each month and is where you might see stories about the warmest August on record, or the where does 2020 rank among recent years in terms of global temperatures. It's also really important to note that there has been a major international effort to assess the field of climate science. The Intergovernmental Panel on Climate Change, or IPCC, was commissioned by the UN Framework Convention on Climate Change to assess the state of the science around climate change. And they recently released their sixth assessment report from a working group focused on the fundamental climate science. This report came out in August of 2021. And one of the primary conclusions here is that climate change is already affecting every region on Earth in multiple ways. The changes that we're experiencing are also projected to increase with further warming. That is a really strong indication that climate change is something that we have to grapple with, but also something that human activities have the potential to slow down or even stabilize. All right, now shifting over to climate simulations and the way that we use models to understand the climate system. So NASA has many products to monitor and simulate climate, and you would have seen this in the other RSET trainings, including part 1 of this training, which I've already mentioned. Just to give a couple examples to make sure we're covering all of the bases here, NASA has key products relating to precipitation, such as iMerge. MODIS products get us lots of information around temperature and vegetation. We have products on soil moisture like SMAP. The Orbiting Carbon Observatory tells us about carbon fluxes and exchanges and pools. And then, of course, we would look to things like the National Snow and Ice Data Center to understand sea ice and other elements of the cryosphere. This is just a very small sample of a much larger set of cutting-edge remote sensing and observational products that help us understand the climate system and observe its changes over time. Of course, NASA is also taking these data and building physical models that help us to connect these observations and fill in gaps between these observations. So we wanted to expressly call out the NASA Modern Era Retrospective Analysis for Research and Applications, now MERA-2, and the NASA GISS Model E, which I will talk about more in a moment. This is one of the premier NASA Earth System models. There is also a set of global daily downscale projections produced by the NASA Earth Exchange, which we will discuss later as well. These are just some to call out among a larger set. When we're talking about these models and these observational products, what we are doing is we're trying to cover and understand different components of the climate system and the drivers that might cause changes in this climate system. So what you see on the screen is a simple cartoon showing some of the major features of the climate system. Of course, you might immediately think of the atmosphere, the chemical composition of the atmosphere, clouds, sunlight, the temperatures and rainfall that you might get within that atmosphere. Of course, the climate system also interacts with the oceans, the vegetation and biosphere, the ice and snow cryosphere elements of the climate system, and of course, land and surface hydrology. All of these are parts of a larger climate system. And what you see on the screen also are some of the things that can drive changes in that climate system. For example, there may be changes in the sun. There may be changes in the way that our industry puts out greenhouse gases, or agriculture, or deforestation, for example. All can do this. There are also other drivers like volcanoes that can change aerosols and other components of the atmospheric chemistry to have strong interactions. So we are building our models to try to understand this system and the way it will respond to these types of driving changes. The way we do this, one of the primary ways at least, is to build climate models. And as I mentioned before, one of the premier NASA models is the NASA GISS Model E. Climate models are built on fundamental principles of physics and chemistry. They represent the climate system in all of its elements through grids and fundamental equations that are three-dimensional around the world, up into the atmosphere, down into the oceans, and representing major components of ice and land and biosphere. These fundamental equations seek to balance across key budgets like water and energy to make sure that we're conserving mass and energy in the system. They are also driven strongly by initial conditions and the boundary forcings and other drivers, things like sunlight or land use or greenhouse gas emissions that can change the system in terms of the energy coming in or the chemistry of the atmosphere. We also tune these climate models using surface stations and remote sensing data sets using advanced machine learning processes, which allow us to use our remote sensing observations to build better models. We also independently validate these models against observed trends and variability, and look to these models in particular to extend beyond those things that we can directly observe. That means filling in spatial and temporal gaps, but also going to conditions that are hypothetical pathways of society and other changes that could come with climate change. Of course, models themselves are subject to limits in predictability, especially models of the atmosphere, given the chaotic nature of the climate system. That means that we are limited by the spatial resolution, and even some of the fundamental physics limit our ability to make accurate predictions and to actually observe and capture every process. Of course, to do something on this scale requires computational systems that are some of the most powerful in the entire world. The NASA Discover supercomputer that you see on the screen is one of several supercomputing centers that are running atmospheric and other climate models. And this technology enables better and better models over time and allows us to ask more interesting and useful questions. As I mentioned, over time, with the computational power and advances in climate science, we have been able to increase our resolution and our ability to represent specific processes within the model. So here is just a demonstration of some of the typical climate and atmospheric models that you may have seen over the decades. So back in 1990, it was typical to find individual grid cells on the order of 500 kilometers. And what you see on the screen is the elevation of Europe. And you can see that it was a coarse representation back in 1990. As we go forward in time, you'll see these resolutions increasing and starting to actually pull out features that we would recognize as the Alps or the Atlas Mountains or Greenland's ice sheets, not to mention some of the internal coastlines. So this type of improvement has gotten us far, and of course there is always more to go. And these can be even further extended using regional climate models and empirical models that use statistical approaches to get to finer resolution. So here, for example, is the type of representation you might have in a regional model at 30-kilometer resolution, where now you are seeing some of the sub-mountain ranges across Europe. And these things matter when it comes to circulations and extreme events and other energy exchanges. As an overview of this, climate models have advanced since 1990. The typical model resolution has gone from 500 kilometers back in the first IPCC assessment to now the models that we use in the IPCC 6th assessment tend to be around an order of 100-kilometer resolution, with regional models getting down to 25 to 50-kilometer resolution. The components of the climate system that we include have extended from atmosphere, ocean, radiation, and land physics and sea ice to now adding additional things like detailed atmospheric chemistry, shifts in land use and land cover, land and ocean biogeochemistry, and improved interactions between aerosols and clouds. In general, it's important to go back and recognize what climate models were designed to do. They were designed to understand the climate response to combined or individual driving factors, such as understanding how methane is a different greenhouse gas than carbon dioxide. We also, of course, look to climate models to understand the impacts of policy choices, like large-scale greenhouse gas emissions policy, but other things like air quality, for example, I'll show in a moment. We also can use climate models to get an idea of the types of climate changes that are coming as a forewarning of a need for adaptation. And this can be done in conjunction with local vulnerability assessments. And as we'll show in the second part of this presentation, the climate models begin the conversation, but further information is needed before action can be taken. They're also quite good at understanding the potential impact of known unknowns, or things that we know are important but cannot specifically predict. For example, in the historical record, we have seen large volcanic eruptions that can have major influences on the climate, such as Pinatubo. And we know that these things are likely to happen again in the future, even if we cannot predict them at present. We can run them as potential hypothetical scenarios. It's also important to recognize what climate models are not particularly designed for. Climate models are not what you would use to make perfect short or long-term predictions. As I mentioned before, there is a chaotic nature of internal variability and imperfections in the models and data. Not to mention, if we're making a long-term prediction, we have to also understand uncertainty in things like the economics behind greenhouse gas emissions and land use change. This is another example. If you wanted to know what the forecast would be for this weekend, you would look for a weather model rather than a climate model, as it would be focused on those types of smaller scale interactions and dynamics. Climate models are also not able to solve political issues or ethical quandaries. There is no calculation on ethics in any subroutine, for example. So we rely on scenarios to understand the ramifications of different political or ethical choices. We also do not look to climate models to understand truly local information given those scale issues. Models tend to be evaluated primarily at larger scales, even beyond those specific grid point levels. And the information below 100 kilometer is not necessarily going to be reliable in the near term, because we are representing some processes there, but there is a lot more calibration and validation to be done. Climate models are also not particularly capable of understanding what we would call unknown unknowns. For example, models that were run in 1970 did not know about ozone chemistry and therefore did not know about the stratospheric ozone hole. There is, of course, the potential for similar unknown unknowns to emerge, and recognizing that potential shortcoming is important as we manage risk in the future. In terms of climate simulations, of course, we use our climate models to understand historical and future climate. One of the most important things to do is to determine the human influence on the climate system. So what you see on the left is a figure from the recent IPCC Working Group 1 summary for policymakers. And in the green cloud, with the green line, you'll see simulations using climate models where only natural forcings were included, such as volcanoes, solar cycles, and changes in the axis and orbits of the Earth. This produced a fairly stable climate with wiggles, but generally keeping global temperatures around the historical conditions. When we look at the actual observations in black, we see that there has been a divergence from this green cloud. And to represent that observed trend, we have to include human factors such as the greenhouse gas emissions, aerosol emissions, and land use change. When we do factor those human influences in, along with the natural variability, we end up having a much better representation of the climate changes that we have observed since pre-industrial conditions. This knowledge that humans are influencing the climate system also motivates looking forward into the future. And one of the fundamental ways to understand this future projection is by the overall amount of carbon dioxide emissions. The overall amount of greenhouse gases that we put into the atmosphere will in many ways determine how far climate change will occur. In this graph here, also from the IPCC, you can see the historical conditions up until the early 21st century, and then several scenarios going out into the future. These are a set of scenarios sometimes called SSP-RCP scenarios, meaning shared socioeconomic pathways representing socioeconomic development, things like income or technology or land use or governance, independent of climate change. Whereas the RCP component, which is the second number here, 1.9, 2.6, etc., is what we call representative concentration pathway, which talks about the greenhouse gas levels in the atmosphere and their evolution over time. And this set of pathways also includes information around greenhouse gas emissions, aerosols, and carbon fluxes from natural sources. As you can see, these SSP-RCP scenarios extend further out towards the right here, meaning more and more CO2 emissions as we get out towards this SSP 585 scenario. With that increase in carbon emissions, we also see corresponding increases in the global warming levels. And the question for policymakers is, how far will we go in terms of burning greenhouse gas emissions? We can take those same scenarios and run them out into the future, out to the end of out to the year 2100, and look at the global warming, the global temperatures that follow. And what you see in this chart are the various SSP-RCP combinations, and the solid line here in the middle represents the ensemble mean, and you have a spread from the climate models representing some uncertainty within each of those climate models. In this case, we're drawing from a large set of climate models that are organized by the Coupled Model Intercomparison Project, or CMIP, which has about 50 modeling centers and around 100 distinct models that have produced some level of output. But what's important to note here is that the spread across the climate models is still smaller than the spread between the pathways, whether we have a high mitigation and therefore low greenhouse gas emission scenario, or whether we have a low mitigation scenario with higher greenhouse gases. The uncertainty across the climate models is less than the uncertainty of which pathway society will take. Another way of representing this has picked up a lot of attention, which is these global warming stripes. And this is a way of representing the historical and future projections of temperature on a global level, with each year represented as a vertical stripe with the color of the global temperature. And what you see here is from pre-industrial conditions towards today, we have this dramatic increase in terms of the amount of pink and red years, suggesting that showing that the global warming levels have increased. We get out to this mark here where it says today, and we face 5 representative pathways that we can choose to go down, depending on actions that society might take. In this very low emissions future, we would be facing this type of set, this set of red stripes, suggesting that it will be warmer than the past. But this is still in stark contrast to a middle or a high emission scenario, where you end up much deeper into these dark reds, showing much warmer global temperatures. So this amount of pathway dependence, and within them, the spread across here is different climate models in terms of how deep and how early those reds might appear. This gives us an idea of the choices that society is facing. If we take a spatial approach and look at this, we'll see that the climate projections can be done using these scenarios and then determining which time we're looking at. So in this case, we're looking at a mid-century, 2041 to 2060 period under a moderately high emissions SSP 3-7.0 scenario. And you can see that in this mid-century period, we have a pattern of warming that is accentuated and deepened when we go to the end of the century. Some of these patterns are quite strong and scale generally with the global warming levels. Another way of looking at this is by looking at specific levels of global temperature. In this case, this is the map when the global warming level reaches 1.5 degrees, and the bottom row is when it reaches 3 degrees Celsius. And you can see temperature on the left and precipitation on the right. Again, these charts coming from IPCC. And you'll notice, again, some of the patterns are consistent across different global warming levels, And these patterns are fairly robust, regardless of which scenario, which pathway we take to get there. So these are the worlds that we are choosing between. It's also, of course, important to recognize that climate change does not stop at the year 2100 just because some of these charts do. And the chart you'll see on the screen at the bottom now is the global mean sea level, and it's the change relative to the year 1900. And in this case, the chart has gone out to 2100 and shows a fairly tight spread. But if we were to extend this out to the year 2300, you can see that the spread becomes much more dramatic. Even this high mitigation scenario that involves substantial effort to reduce greenhouse gas emissions has large global sea levels that will likely spur risk and actions along coastlines. The high emissions scenario goes much further and even extends off the chart here, where the IPCC could not rule out sea levels greater than 15 meters, for example, by the year 2300. This is because some components of the Earth system, especially ice and deep oceans, take a long time to respond to global warming. And in that sense, until the Earth climate system comes to an equilibrium, you could see continuing changes in these factors. Another way of representing this is by looking at the spread of climate projections owing to different sources of uncertainty. What we refer to here as internal variability are things like weather and other chaotic patterns within the climate system that tend to go up and down on a internal mode. And you can see that in the early years, this type of uncertainty dominates. And that's another way of us saying that in the first decades beyond present, what will happen is largely dependent on these internal fluctuations in the climate system. However, as we go further out into the future, those fluctuations don't really get any bigger, while things like uncertainty in the models start to become more important, this blue level. And then as we get further and further out into the future, as we mentioned earlier, the spread between the scenarios, the actual pathways that we choose, become the dominant source of uncertainty. A fundamental principle that's important to know is that each climate model has a slightly different response to greenhouse gas emissions. This is the sum of many internal dynamics and process representations, but we refer to this as the equilibrium climate sensitivity, which is the equilibrium or steady state change in the surface temperature following a doubling of the atmospheric carbon dioxide concentrations from pre-industrial conditions, which is another way of saying that if we have a fundamental doubling of this important greenhouse gas, what is the climate response? We can look across different climate models and see some have high equilibrium climate sensitivity, which means they warm up very quickly with greenhouse gases, and others have a lower equilibrium climate sensitivity, which means they have a slower response to that greenhouse gas. But overall, we see a distribution which suggests that there is a likely range and some low likelihood higher and lower models. And this uncertainty is important to recognize as we go out into the future. It's also very important to note that climate models are useful beyond these core greenhouse gas sets of simulations. For example, we use climate models to look at the potential for low likelihood, high impact events like a major volcano or a shift in some ocean circulation pattern. We also can use them to look at air quality and energy policy. For example, in this example simulation, there was a policy for widespread electric vehicle adoption, which caused greenhouse gases to come not out of, aerosols to come not out of tailpipes, but from localized power plants. And this changes the type of aerosol that you might get from burning at power plants compared to in a car's engine, and led to a shift in the overall aerosols concentration around the world, resulting in changed atmospheric forcing across the world with patterns that we can simulate here. So this ability to understand the ramifications of a policy in terms of air quality and overall climate impacts is important even on the short term. Another set of applications for climate models is to go back and look at ancient climates, what we would call paleoclimate, which is the simulation of things like ice ages or mega droughts that were many decades or centuries or millennia ago. There is also very exciting new applications around understanding the climates of distant planets. Here, looking at exoplanets orbiting distant stars. And here is a simulation of a planet called Proxima Centauri b. And this is a planet that is tidally locked to its star, which means it does not rotate the way that we would think about it on Earth. The sun is always hitting one point on the planet. And here we've just imposed the Earth's geographical pattern, but you can see the effect of having two different places where the sun hits, whether it were to hit on the longitude equivalent of Central Europe versus a longitude equivalent of the middle of the Pacific Ocean. You have different patterns in terms of how that energy is spread across the planet and different patterns of what the temperature might look like. And this is important not only to understand these fascinating places, but as we think about what life might look like and where it might fit and sit on planets such as this. In terms of using climate information to go to impact and risk sectors, we want to begin by looking at how we think about risk. In general, we are in this presentation here focused on climate information, coming from natural sources and coming from human influences. This climate information tells us about climate hazards, but hazards are one component of risk that must be combined with vulnerability and exposure. This intersection of a climate hazard with a vulnerable system that is exposed to that climate hazard creates what we think of as risk. And this is where you would expect to find impacts. This is something that is in turn affected by socioeconomic processes. So for example, if the hazard we're interested in is drought, the extent to which a farm is vulnerable to that drought may have something to do with the way it has been designed and invested upon with the background of economic and market situation. And then whether that farm and the overall breadbasket is in a place that is exposed to drought gives us some semblance of the overall risk. And of course, these things can be modified by adaptation or mitigation actions, and governance can be something that sets enabling conditions. It's also important in recent work, there has been an emphasis that responses to climate change, such as adaptation or mitigation, can in turn also affect risk. That is something to understand. We, of course, are interested in climate risk and impacts across many different sectors. So I'm going to very quickly go through some of them. Here is an example for terrestrial ecosystems, where, for example, we are currently monitoring fires across much of the Western United States. We also use climate information to understand risks to marine ecosystems, such as the mangroves in Belize, pictured here. We look at climate information related to water resources applications so that we can understand, for example, why Lake Mead levels in August 2000 were so different than they are in August 2021. We also use climate information to look at food systems, both in terms of the way they interact with forests and deforestation, but also to understand how the management and use of farm equipment affects the climate system, but also how that management produces healthy crops and supplies markets and in turn feeds healthy and growing populations. We also look at climate information in urban areas. Here is an example of a subway stop within New York City showing the after effects of Hurricane Sandy, which came and flooded this station, leaving debris even up on top of these signs. This type of information helps in many aspects of urban planning and resilience building. We can also look specifically at human health and climate effects on human populations. In particular, here we're looking at a map on the right that is looking at heat vulnerable neighborhoods represented in blue, and the red areas, which are hotspots of heat within New York City. Of course, where you have hotspots of heat and large local vulnerability is where you might expect the largest risk. It's also important to recognize that climate is a background condition for a lot of development, and many people's livelihoods are very closely tied to climate systems, such as this population in informal settlements in Dhaka of Bangladesh. When we look to make impacts and risk projection, we try to follow a framework that produces solid results for climate action. The first thing that we're going to do would be to represent the current system of interest. And as I'll show in the future slides, we will follow each of these steps. The second thing will be to represent current climate, then look at how the system changes in the future, so that when we project our future climate, we are attaching those climate conditions to the system of the future. We then project future climate impacts so that we can identify and test adaptation and risk management strategies. This fundamental framework we will now describe in a little bit more detail. So the first thing to do would be to represent the current sectoral system. Here is an example of a farm system. And you might have a farming family with their own details in terms of gender and demography and income and connections to society and markets, etc. But they may be growing a certain crop with certain nitrogen inputs and access to water or energy or farm equipment. Understanding the specific elements of a system, the conditions and the lifetimes of the system components, the ability of that actor, in this case the farmers, and their motivations, and the boundaries of the system. For example, where do they take their crops, and what type of market influence might adjust the way they run their systems. All of this helps us better understand what is being impacted if climate change affects this location. Of course, we also have to represent the current climate of that system, and as we've seen before, there are many ways we can do that in terms of various NASA products. But the goal here is to characterize the current climate conditions that that farm system or similar thing would be exposed to today. We then look to understand that climate system, not just on the most prominent types of climate information, but we would look to inventory the different types of climate responses that might be important. And here we'll introduce this concept of climatic impact drivers, which are climate conditions that directly affect elements of society or ecosystems. And it's important to note that these climatic impact drivers, or CIDs, they can have positive, negative, or inconsequential outcomes depending on the region in the system that is affected. And here's an inventory of the types of climate changes that you might want to look at to understand how your system may be vulnerable. And you can see this includes things related to temperature, like average temperatures and extreme heat, and of course things like precipitation and floods and droughts, and extends further into snow and coastal and ocean effects as well. One of the important things is to recognize that systems often respond at given thresholds that are particularly related to the tolerance of a system, whether it's a biophysical tolerance or an engineered tolerance. And here you are looking at a chart showing a particular heat threshold, which is coming from NOAA, the National Oceanic and Atmospheric Administration. The NOAA heat index is a combination of temperature and humidity. And when that index exceeds 41 degrees Celsius, it is considered dangerous. This condition, as you can see, has a very different distribution in terms of the number of days per year that you would be in this dangerous condition. If you look in your own part of the world, you might see that it is strongly dependent on which of these scenarios we follow and whether we're looking in the mid-century or end of century. In this case, at the end of the century, under a high emission scenario, there are many parts of the world that are routinely exceeding this dangerous condition. And this is important, of course, for human health, especially those who are looking to do outdoor exercise or construction or agricultural labor. When we're looking at future climate, it's important to look at the intensity of climate changes as well as the frequency of extreme events, the extreme event duration, the seasonal timing at which events may occur, and the spatial extent in terms of whether you will see extremes in parts of the world that have never seen them before. This relationship to tolerance threshold is important. And what you see on the right here is the projected number of hot days. In this case, we're using a Fahrenheit scale. But when the maximum temperature exceeds 90 degrees Fahrenheit, you can see that in the baseline, in the historical period, it only happened 18 days a year. But under upcoming decades, you start to see this event occurring more than 25 days per year, nearly 50 days per year, and up to 76 days per year, even in the central estimates going on to the 2080s in this New York City example. We can also represent climate extremes in terms of particular extreme events, like a 10-year heavy precipitation event. In this case, we're looking at an event that is expected to occur once every 10 years on average. And in the pre-industrial conditions before human society had dramatic influences on the climate system, this would have happened only once every 10 years. But as we go into warmer and warmer global temperature conditions, up to a 4 degrees global warming level, this event would happen almost 3 times every 10 years. Another way of looking at this would be to understand what would be the new 10-year event under each of these conditions. And in that same 4-degree global warming level, the new event that would happen once every 10 years would be 30% wetter than the current condition that happens once every 10 years. So in this sense, we understand both the frequency of an extreme event happening more often and also the intensity of that extreme event should it occur at the same regularity. We also want to emphasize that sometimes it's easier to have strong and robust statistics over broader regions, such as this graph from the US National Climate Assessment showing changes in extreme precipitation under a low and high emission scenario. Here it's assessed on broader multi-state regions. That is very useful to draw out large patterns. But it's important to recognize that oftentimes adaptation responses and actions are taken locally. So there's a trade-off in terms of some of these scale decisions. Another way of looking at this would be to remember that we have many climate models. And in this case, we're looking at core changes in temperature and precipitation for a county in Alabama. This is Henry County. And what you see with this black square is the historical condition. And there is a green cloud representing near-term projections, showing warmer conditions, but a spread in precipitation. And then as you go to the yellow cloud and brown cloud representing mid-century and the red cloud representing end of century, you can see that there is strong agreement in warming, but not strong agreement in terms of the precipitation. Some models are wetter than present day. Some models are drier than present day. And you could even distinguish between circles and triangles in terms of which scenario in terms of emissions. But some of these larger patterns are important to recognize, as well as the uncertainty. Another thing that we do with our observations and our climate models is we combine our best understanding of present-day climate with our projections of climate changes to produce what we will call bias-adjusted climate projections. These use the models and the observations to compare in the historical period and determine what are those climate model biases. Could be things like the intensity, frequency, or the distribution of extreme events, or the finer spatial patterns lower than the grid scale of the climate model. We can then adjust the climate model projections to counteract these biases to impose stronger, more observationally consistent patterns in those coarse global models. The benefit, of course, is that this reduces many of the biases that are important to sector responses. However, there are also drawbacks. For example, assuming that the historical biases are the same as those you would find in the future. It also depends on having strong observational data to determine those biases, and therefore is limited in areas with poor observational coverage. Whenever we do a bias adjustment, it's important to note that statistics are used to make these adjustments, and only statistics that are within focus are going to be affected. However, others may not be. So it's important to know the methods that are used, because especially they can lead in their adjustments to temporal, spatial, or internal inconsistencies in those adjusted data sets. Here's just an example. The NASA NEXT high-resolution climate projections are already out for CMIP 5, and there are CMIP 6 projections coming soon. But even in CMIP 5, there were projections for temperature and precipitation using 4 different methodological approaches, 30 different models across the major scenarios with global coverage at about 25-kilometer resolution and continental US coverage down even to 800-meter resolution on a monthly scale and 6 kilometers on a daily scale. When we go to that future, it's important to recognize that there are changes in the future system. So if we revisit our farming family, it's important to recognize that by the time we get to mid-century, this farm may have invested in livestock, or may have new vegetable gardens or intercropping or something that makes that system different than what we have today. That future system may therefore respond differently to what we have today. This approach to understand how climate will affect future systems is one of the motivations for using additional impact models such as crop models to understand climate impacts on future systems. Here is an example of an upcoming study by Jonas Jägermeier and colleagues that was done as part of the Agricultural Model Intercomparison and Improvement Project and the Intersectoral Impacts Model Improvement Intercomparison Project. That's AgMIP and EasyMIP. Their projections of corn or maize production at the end of the century under a high emission scenario show yield losses across much of the world, but also pockets of regions where there could be yield increases due to local management and local climate conditions. These types of impact projections are important to examine using current and future systems to understand how those are also changing. And this type of information becomes important because of international trade and large-scale changes in terms of the way that food and other commodities flow around the world, create interest on a local level all the way up to the global level. It's also important to recognize that projections become increasingly uncertain as you move further into the impacts realm. Here's an example of a project that was done, again, with the AgMIP group, looking at wheat and cotton yields in Pakistan. And in this situation, we had temperature projections that you can see become more uncertain as you go into the future in a high emissions and moderate emissions scenario. The precipitation projections were also quite uncertain across the whole century. This led to projections of bread, wheat, and cotton yield declines. But this spread here now includes the spread from multiple climate models and multiple crop models under both of these emissions pathways. Representing that uncertainty is critical as we're making our adaptation and risk plans to recognize what we have confidence in and what we have still cause to plan for in terms of uncertainty. In terms of climate change adaptation, once we have this type of information, it becomes a new challenge to determine what types of solutions and what type of alternatives we might come up with. In many ways, climate adaptation must be targeted to these specific climate hazards and tailored to the specifically affected system to be most effective. In this sense, we're also interested in adaptation timescales to understand whether the adaptation we're going for is something that would react to an ongoing crisis or to be proactive in terms of anticipating future concerns. Both of these approaches have benefits and drawbacks. In terms of producing these adaptations, it's important to recognize the context of the current system and the people who are making decisions and affected by the current systems. For example, it's important to recognize that there is already existing infrastructure, investments, and connection between the impacted system and others. It's important to recognize that decision makers often have multiple and sometimes competing motivations beyond just the climate sphere. And adaptations can benefit from integration into natural cycles of investment, updates, and maintenance of equipment in terms of recognizing when action can most efficiently be taken. Adaptation is also a continuing process that is bolstered by solid scientific information. It is not a one at a time, one and done action. It's usually something that has to be revisited as more climate information comes along and as impacts and systems change over time. As we're thinking about adaptation, it's important to recognize that adaptation actions that are targeted to a specific climate hazard will have a clearer benefit than those that are taken in general to improve the performance of a system. This schematic is drawn from a paper by David Lobel and looks at crop yields in response to some kind of stress. So just for simplicity, let's take heat stress, meaning this is warmer temperatures on the right and cooler temperatures on the left. In the initial climate in the present day, we might be at location B. So we have a current crop system, and as temperature goes up, that crop system is due to decline in yield. However, we might take some action to increase the overall levels of yield by modifying the system. So for example, this might be higher nitrogen levels for more fertilizer. That increases the yield. However, you'll see that as we go into a future climate situation, there is a corresponding loss of yield that results in this increase in fertilizer having the same effect in today's climate as it does in the future, which suggests that the fertilizer is a benefit for the agricultural sector that does not really directly respond to the climate challenge. In contrast, we may have a situation on the right where we have the same current system at this location B in the current climate. And here now maybe we modify the system to plant at a different growing season start date, so an earlier planting date, for example. This may have a small benefit today, but as the temperatures increase, this has a larger and larger benefit as that climate change occurs. This would be a good example of an adaptation in the sense that the action taken directly responds to the climate threat and results in a larger benefit in those changing climate conditions. We can use the same approach in our global crop models to understand the benefit of specific adaptation types. Here again, looking at the crop models that were organized by AgMet. The pixels that you see on the screen represent the benefit of selecting an alternative seed variety that is more in tune with the future climate conditions, especially the average temperature as climate change occurs. Where you see deeper greens are places where that reselection of a new seed variety has stronger benefit under that future climate condition. This helps us identify those places that have the most acute need and also where the benefit may be the greatest for some kind of adaptation like this. Another example of adaptation work is around the idea of creating a space for adaptation actions. And here we'll spend a couple slides to look at a case study, which is the New York Panel on Climate Change. The NASA scientists at NASA GISS facilitated a consortium of New York City agencies and private corporations, as well as academic leaders from the tri-state area, to convene and discuss climate information and prepare the city for climate impacts. Here is a photo showing one of the NASA GISS scientists, Cynthia Rosenzweig, along with New York Mayor Michael Bloomberg back in February 2009. This activity was promoted at a very high level within the city, which allowed these discussions to get deep into operations and vulnerability planning. One of the things that this New York panel on climate change recognized was that the New York City coastlines were particularly important places when it comes to things like water treatment plants. These water treatment facilities are not evenly spread out throughout the city, but are located especially on the banks of the rivers and along the coastlines. This means that these water treatment plants are particularly exposed to coastal flooding and storm surges, such as those that might be exacerbated by sea level rise from climate change or by tropical cyclones and hurricanes that could hit New York City. This work identified a challenge of water treatment facilities as a particularly vulnerable and risky part of climate change, especially when we saw that there had already been events where there were flooding along water treatment plants at the coast. For example, this photo of a backed up water treatment plant in the Bronx. When we identified this as a challenge, that motivated the mayor and his agencies to lift water treatment plants and install pumps at higher elevations so that the coastline was better prepared for the potential of a major hurricane that could have coastal flooding in New York City. Of course, this was done back in 2009, and a couple years later, Hurricane Sandy made its way towards New York City. Hurricane Sandy also was identified as the type, or as an example of the type of event that could lead to problems in hurricane flooding for subway systems. And here on the left, you'll see a map of the subway tunnels that flooded when Hurricane Sandy came through. This was another thing discussed within this report. And as you can imagine, this led, when Hurricane Sandy did come into massive subway flooding and other big problems in the area. So this example of NASA scientists working with public, private, and academic partners to identify the types of challenges that could happen under climate change situations and interacting with extreme events helped New York City prepare for Hurricane Sandy. We had a chapter also on transportation, for example, that looked at subway challenges. This also meant that when recovery funds came to New York City to build back a more resilient coastline, the New York Panel on Climate Change had the climate information that was facilitating that type of planning effort. And that report was ready to go and right in the aftermath of that devastating storm. So to summarize, climate information products can support mitigation, adaptation, and risk planning within strong scientific frameworks. NASA products support improved understanding of the climate system. Climate applications also require selection of fit-for-purpose models and data sets. And the impacts and risk from climate affect many aspects of nature and society. If we look at historical climate and future climate projections and sectoral conditions, that can help drive planning and make more scientifically robust strategies for the future. Climate decisions, of course, are facilitated especially by tailored climate information that recognizes the system, vulnerabilities, exposure, and local context of decision makers. And we do want to thank also the NASA Climate Adaptation Science Investigator Work Group, CASSI, which is preparing climate adaptation and risk plans for NASA facilities, and also helped in this effort to build climate literacy across NASA and the audience. And we are really thankful for your attention today. If there are questions now, we would appreciate it if you could enter your questions in the Q&A box. We will answer them in the order they were received, and then we will post this Q&A to the training website following the conclusion of the webinar. Also, for information, if you would like to have further discussion with myself or Dan Bader, you can find our information here. And there's more information on the training webpage for RSET and the broader RSET website here. Thank you very much. And we have one more slide here just showing some of the key resources that you might consider looking into as you pursue climate information for your own applications. Thank you so much.
Great. Thanks, everybody, for sending in so many terrific questions. We've been trying to answer them as they come in. We do have both Dan Bader as well as Alex Lorraine here to answer any of the questions that have been coming in. So do keep them coming, and we appreciate it. So question number 1, the resolution of climate models is improved thanks to higher resolution satellites or thanks to higher calculation power. Alex?
All right, yeah, thank you for that question. The answer is, of course, both. We have benefited in multiple ways from having the improved observational systems that we have in terms of satellites and ground-based networks and airplanes and everything that we put out there. That gives us a better understanding of the fine-scale features of the climate system, which means we can improve our physics and the overall representation of these processes in the models. Of course, that improved understanding wouldn't be possible to actually simulate unless we had these higher performance computers. So with better physics and with better computers, we're able to put those two things together and have better simulations. And we know that there's higher potential to go even further. For example, as computational systems improve, there are more things we'd like to get into our models, and we're working on that every day.
Great. And this question number 2 has to deal with more a regional analysis. So the question is, how can I assess the effect of climate change in a specific region on a local scale using Earth observations? And for how long of a period should the analysis be carried out? So
the first part of this RSET training went through a large list of the resources within NASA and NASA's partners that could be useful in this type of application. So there are observational products related to specific aspects of the climate system that you may be interested in, like temperature or rainfall, ocean salinity, snow, ice, fire, and others. So you can take those products to characterize the current climate system. And we would recommend that you find at least 20 years of data to capture robust statistics, whether you're looking at long-term trends and average conditions or some kind of distributional change, for example, a shift towards more extreme events. I noted in the text on the screen that, of course, climate phenomena can occur on very fast or slow timescales. You know, something like a tornado is a strong weather event, but the statistics of how frequently tornadoes occur and where they occur and what season they occur is something that we might study with a climate approach. So we need a large number of years to capture those statistics. And if you're interested in something like a rare extreme event, like a 1 in 100 year flood or a extreme heat wave, you may need even longer to understand what's going on there. So, for example, at NASA GISS, we have researchers looking into mega droughts and long-term drought conditions. Those need longer times because of the scale of those conditions as well.
Great, thanks, Alex. And question number 3, what is the ideal climate modeling for maritime countries such as Indonesia compared to a landmass such as, say, the United States or Australia?
So Indonesia is a great example of a place with a large amount of ocean land contrast and high mountains, and it's a place where applications are often drawn to regional climate models so that they can capture those complex land-sea circulations and the influence of mountains and coastlines and diverse land covers. Of course, regional models are also useful over those big continents like North America or Australia. For example, mountains in the Rockies or complex coastlines in South Australia, things like that. So in general, regional models add important local detail, but are still driven by the large-scale patterns from the global climate model. So there's a question I think we'll get to in a minute that will go further on this. But in general, you have to be asking whether the benefit of that regional model outweighs the potential kind of loss of quality as you're putting more and more models together, you can sometimes lose that signal as well. So finer resolution is not always a better signal and more useful information, but it is something that is important to ask whether the phenomena you're after, the decision that you're making, is likely to be influenced by those fine scale features, and in a place like Indonesia, oftentimes it is.
Yeah, and Alex, to follow up on that, this next question also kind of follows up on that issue of resolution. So how does one downscale climate models, and what is the highest resolution that can be attained?
So here we've written out an example with some generic numbers here. Of course, when people do this, they are much more specific on this. But if we take a climate model that's run on a global level, for example, at 100-kilometer resolution, or around 1 degree resolution, we might use that climate model output as a boundary condition to drive a subsequent regional model, maybe at 30-kilometer resolution. And you can keep this process going. You could then embed another model that has a 10-kilometer resolution, and you can keep going all the way down to your finest resolution atmospheric model if you so chose. There are atmospheric models that are used within city blocks, for example, to look at wind circulations, coming around skyscrapers and block by block, things. So you can get down to very, very fine resolution if you wanted to. But there is this degradation of the signal with each model, just because of the effects of translating from a boundary into a finer grid and other things that the physics have to carry through. So just because we can scale down to very fine resolutions doesn't mean that it's always the most useful thing to do, especially if you have limited resources for computation and analysis. Or the observations that would validate those models. So we recommend choosing your resolution depending on the application you have in mind and the likelihood that some fine resolution process or geography will have an influence. A major challenge, just to say that this process going from coarse resolution down to fine resolution is not always a smooth and linear one. There are times where there are fundamental changes in the way we approach the meteorology or the climate processes. And one of those I'll just mention, which is that when you get below about 8-kilometer resolution, the model starts to need actual physics around convection in the atmosphere. Things like thunderstorms have start to be directly resolved, and therefore you introduce a whole other set of physical packages, which can be very interesting, but also have their own sets of biases that have to be understood. So there are these kind of steps and bottlenecks, in terms of as we're downscaling, that we have to keep in mind.
Thank you, Alex. Question number 5. Which climate models do you use? Are they open source? Also, which programming languages are they developed in? So
maybe I should answer this myself. So the climate model that I use is the NASA GISS Model E, because that's where I sit at NASA GISS. But in most of our applications, we are using an ensemble of climate models that come from the 6th Coupled Model Intercomparison Project, or CMIP-6, which was mentioned in the presentation. CMIP-6 has around 100 models from about 50 different modeling groups. The models are all documented in peer-reviewed publications, and many are open source and freely available, including Model E. The models tend to be developed in a variety of languages, but most often I've seen models using Fortran due to its computational efficiency. These models have been made available and used, of course, not just at the modeling centers, but in a network usually of model users across public and private and academic institutions. And usually those models benefit from all of those different user groups that contribute and in terms of code development and validation.
Okay, question number 6. What does the 0 indicate in slide 24?
All right, so slide 24 was looking at those climate stripes. And when we went out into the future pathways, there were a couple lines on there. So this question is looking at a 0 line in slide 24. And that 0 line was actually an indication of the net zero carbon emissions date. So each of these emissions scenarios, each of these SSP RCPs have emissions going out towards the end of the century. And in some of the low emission scenarios, not only do human greenhouse gas emissions reduce dramatically, in some cases they reach net zero or even net negative emissions, meaning humans are pulling more carbon out of the atmosphere than they are putting into the atmosphere. So that time is noted on that chart as that 0 line when net zero occurs.
Great. I hope whoever asked that question, I hope yeah, thank you, Alex. The next question 7 has to do with marine ecosystems. So are corals a net contributor to atmospheric carbon dioxide, or do they help in sequestration?
So here I would love to have a marine biologist to double check all this for me, but my understanding is that corals use carbon in their skeletons, and therefore can help sequester carbon from the climate system. And we see that in limestones and other things like that, where those the accumulation of coral skeletons can pull and sequester carbon into the rocks.
Okay, question number 8. Which is the scenario that seems to be the one we follow according to the decisions that are already implemented? Is it RCP 1.5 or RCP 8.5?
So this is a complicated question. I'm going to give it a quick answer here, but the larger issue of pathways is one that I think you'll see in the next several questions. So I'll preface it that way. Most of the scenarios and the pathways that we simulate are quite similar in the current and near-term years, because they all start at the same starting point early in the 21st century, depending on which simulations. That could be 2005 or 2015. The emissions have been among the higher pathways in recent years, but it's not a one-to-one following any given RCP. And the pathways really are more intriguing and interesting when we look farther out into the future. So 10 years out into the future, you can see differences, and especially 30 years out into the future, they really start to diverge. So I would just caution about using the last several years as a predictive way of which pathway we're on, because the bottom line of each of these pathways is that the decisions we're making now continue to determine which one we will follow. I will note that the RCP 8.5 pathway includes assumptions about coal use, which no longer seem to be as practical or as realistic as they once were. So that overall reduction in coal use that we have seen in the world suggests that RCP 8.5 is useful as a high emission scenario and as a pathway of high global warming levels. But in many cases, I'm seeing increasingly RCP 7.0 used as a high emissions pathway. And RCP 8.5 still tells us a lot about the response of the climate system, and how it would work at different global warming levels. But the exact timing of some of those things you see in RCP 8.5, people are increasingly questioning. So RCP 7.0 is definitely one you should consider.
All right, thanks again, Alex. And the next one, very specific to the country of Mexico. Currently, there are a number of series of scenarios that have been generated around the world. In your case, which is the best scenario for Mexico?
So here, I can't claim to be an expert on Mexican scenarios. What I will say is that whenever we're looking at a specific region, it's important to recognize that there are a variety of climate models and a variety of scenarios. The first thing I would say is that you should be looking at multiple climate models and multiple SSP RCP scenarios so that you can understand the climate and pathway uncertainties. There are downscaled scenarios that include Mexico. For example, NARCAP, which is the North American Regional Climate Change Assessment Program, I believe. and CORDEX, the Coordinated Regional Downscaling Experiment. Those may have scenarios that you would be interested in for Mexico. Although at some of those domains, they cut Mexico into northern and southern parts. So there may be a need to link those together. The other thing that you might want to look at would be the NASA Earth Exchange bias-adjusted scenarios. Those would be at relatively high resolution and have a consistent methodology across Mexico. So check those out and make sure you don't just take one climate model, but you look at the potential of multiple climate models giving an indication of uncertainty.
Great. Question number 10. How can I assess the effects of climate change on a specific region on a local scale using Earth observations, and for how long should the analysis be carried out?
So this is similar to the earlier question, but what we'll say is that one of the first things you want to do in climate change analysis is assess and characterize the current climate. Here you can use weather stations and remote sensing products, but find the ones that target and capture the key aspects of climate that affect the things you care about. So if you're interested in cities flooding, you might want to look at heavy rainfall events and check that against your stormwater drainage systems, for example. And for that, we have precipitation products that focus on heavy rainfall. And we have others that are better for drought and others that are focused on temperature and therefore might be useful for extreme heat. So characterizing the average conditions, but also the distribution of extreme events is what I would recommend. Then the climate models come along and tell us how the climate changes. So we might see shifts in the trends of average conditions or the distribution of extreme events. And we can potentially use bias adjustment or downscaling to connect those climate model projections into the observational systems and get something closer to the conditions observed on the ground. So that will help us reach the scales of decision making. So in terms of time periods, we would recommend at least 20 years to capture the climate signals and not get lost in the internal variability. And if you are looking at rare events or long-term droughts, you may need longer-term periods to capture that set of changes.
Okay, question 11. Given that climate change is mostly attributed to human activities, how is natural climate change differentiated from anthropogenic sources?
All right, so we can use our climate models to see the signature of different types of climate changes on the climate system. And we can draw those out using our climate models, for example, by setting them up to only include certain forcers. So for example, we can set up our climate models with only natural forcers, things like shifts in the sun's output or volcanoes. And then we can compare those against simulations that also include human influences like land use change or greenhouse gas emissions. And we had a slide that showed the difference between those two and underscored the importance of the human influences in terms of capturing recently observed events. We also can use those to disentangle specific types of influences in recent decades. And then because we understand that, we can understand how shifts in greenhouse gas emissions will influence climate in the decades ahead.
Okay, question number 12. How are policies included in the models?
So policies are included in the models through these driving socioeconomic pathways. The SSP RCP scenarios include things like greenhouse gas emissions policies, land use protections, the investments in things like technological growth or the sharing of adaptation technologies across different countries. These policies are therefore represented in the driving conditions in terms of the amount of greenhouse gas emissions or land use that affects that climate system. We use these representative policy scenarios, these SSP RCPs that we've discussed here, as the kind of fundamental set, but we do have many simulations that are developed to explore specific policy options and their ramifications for the climate system. So we did show, for example, that exploration of electric vehicles, mandates and policies to see what that would mean for the climate system.
And question number 13. Do you know a website that displays paleoclimate changes throughout the Cenozoic or the Pleistocene?
So this one I didn't have a quick answer for you. I think we would have to circle back on that and check with our paleoclimate experts. I don't have a website off the top of my head. So let's see if we can find a better answer to that with some more time.
Okay, and question 14. Is the 1.5 degree ceiling, as indicated by the Paris Agreement, sufficient to check the spate of increasing frequency of climate-related disasters currently experienced across the world?
So the recent IPCC report showed that human influence is already changing the climate in every region of the world, and these changes include shifts toward more extreme events. We also saw as a fundamental conclusion that the changes in these climatic impact drivers will be more pronounced and more widespread with each increment of climate change, which also means with every bit of greenhouse gas emissions. The world is currently about 1.1 degrees Celsius above pre-industrial conditions, defined as the late 19th century. So if the question is whether the 1.5 degree target would be enough to stop what we're seeing today, the answer is actually 1.5 degrees would be more than what we see today, but would prevent the even stronger changes that would happen above that level. When it comes to the climate system, 1.5 degrees is not a big tipping point as much as it is a one stop along this path that brings us to larger and larger changes. So it is a useful policy marker, but from the climate system, we see the changes happening all the way up to 1.5 and continuing to happen after that.
Okay, question 15. As noted in the presentation, sub 100 kilometer information from climate models is not reliable at the moment. What could be the best approach to integrate local data with available climate models?
So what I hope to say in the presentation is that if you have a model that is at a 100 kilometer resolution, you're not going to get information below 100 kilometers. So you would have to use some kind of downscaling approach. That would include things like dynamical downscaling, where you use a regional climate model, or empirical approaches, where you use the large scale climate information from a climate model to predict smaller scale. For example, if you knew that a low pressure system sitting off the coast of Boston was likely to lead to a nor'easter, you might get that information from a coarse model, but then extend it to that finer extreme event. We also use bias adjustment, which is a way of saying that we have local information that is indicative of the likely patterns of conditions and maybe even changes at a finer resolution than the global model is giving us. So bias adjustment, allows us to connect local patterns into the climate model projections, and gives us a way of connecting observations and climate changes from the models.
Thanks, Alex. And question 16. What do you mean by the heat hotspots in New York City presented in slide 40, and how did you identify it? Is it the same as urban heat islands? Can we consider the urban heat islands a form of climate change?
On this one, I believe Dan Bader may be best equipped to respond. Dan, can you get this one?
Yeah, okay, I can unmute myself. Sorry about that. So on slide 40, what you're seeing is areas within New York City that have been identified as hotspots. And that identification can often take place with remote sensing or satellite technologies. Those are just warm areas within the city itself. The urban heat island refers to the phenomena that urban areas, cities, are warmer than their surrounding more rural areas. So New York City, relative to the suburbs and more rural regions outside of the city, does have the urban heat island effect. Surface temperatures are elevated, in some cases it's up to 5 or 6 degrees Fahrenheit, peak of the summer, let's say. Within the city itself, there are cooler spots, parks, more vegetated areas, and warmer areas, central business district areas with darker colored surfaces. So that's really the distinction between the two here.
Great, thank you. Thank you, Dan. And we're going to go to question 17. I'm interested to know the sea temperature at a certain depth and bottom in the past and future. Any advice on where to find the climate data I should use and the equation I should use to do the analysis would be much appreciated.
Thanks for the question. Yeah, so I think this is another one where it's worth us doing a little bit of follow through to give you more specific information about where you can find those data. But I will mention that there is a major program called Argo, which is a set of autonomous buoys. So these are floating instruments that have an ingenious system that allows them to float around with the currents and occasionally dive down into the water column and float at a different depth, and then once again dive even deeper. And each time it does this, it then comes back up to the surface and transmits its data findings. But this gives us information about currents. It also gives us information about the temperature and salinity profile of the ocean, and has really revolutionized our understanding of what is happening within the depths of the ocean. So the Argo floats are definitely a data set you should check out. In terms of the future projections, a lot of these climate models include, pretty much all of them include three-dimensional oceans that have projections of shifts in overall heat capacity and energy in the oceans, but also changes in ocean structure and currents. So you would find that information within the CMIP6 models. And I see the person typing on the screen. Yeah, just please note that all of these data sets, you could say all of these CMIP6 climate models include 3D information as well.
Great. Question 18. Land use and land change classification for relatively large areas incurs errors. For example, if compared with relatively small areas, for example, a city. How can we get the same result for both small and large areas? Please mention models, algorithms, etc. Thanks.
Yeah, so this is a much deeper conversation, but what I can say here is that when we are looking in a region with complex and heterogeneous land use, this could be a region where a regional model makes sense to use. Sometimes we can get much more accurate information in different land covers and land uses with those regional models. Now that said, when we scale up to a larger area, we are often trying to represent the net effect of all of those land uses and land covers within a larger grid cell, and that is done through the use of land cover and land use data sets that are designed to aggregate that type of information into useful quantities. So the way that we can do that, also within our climate models, we often have what are called tiles within each grid cell that represents, for example, open ocean or open water versus forests versus grasslands or agricultural areas, or urban built-up zones. And we can represent the different water and energy balances within those tiles as a subcomponent, which then aggregates up to the total. So there are models that do this to a greater or lesser extent, but we do represent different land use and land cover types within the grid cells as we're doing our water and energy and carbon balances for each grid cell.
And question 19, how is a global climate model differentiated from a regional climate model?
So the answer here is twofold. The first and foremost is that the regional climate model is going to operate at a finer resolution than the global model. Now, the regional climate model will often, therefore, contain more complex, higher resolution dynamics, and in that sense may capture thunderstorms in a way that the global model wouldn't have, or tropical cyclones, just as some examples. Now, that said, the global model is often more of an Earth system model, for example, having more direct representations of the ocean depths and the cryosphere and the biosphere and the forcing information, for example, from different natural forcers. So each of those have a role, but the regional models require global models to drive their boundaries. So once again, just to summarize, I see people typing on the screen. Regional models are at finer resolution. They have some more complex dynamics, but also lack some of the Earth system components that make the global models more comprehensive.
Question 20. As climate changes become increasingly more severe and more prevalent, I imagine many sectors such as public health, international development, etc., will have to adapt to take climate factors into consideration more so than they currently are. What fields of work/study do you think will begin to emerge to address the climate crisis?
So there's some good notes on the screen here about how the IPCC has a working group too, which focuses on vulnerability, impacts, and adaptation. And they break down their impacts into multiple sectors, including terrestrial and freshwater ecosystems, ocean and coastal ecosystems, water resources, food, cities, infrastructure, health, and various forms of poverty and sustainable development and livelihoods. So each of these sectors, there is a tremendous amount of work going on in terms of understanding the vulnerabilities, the hazards, the exposure, and therefore the comprehensive risk posed by climate change. We also recognize that there are systemic effects and unforeseen impacts that can come from extreme weather and climate events. So there are still emerging areas of study. I would say that thinking more broadly, there is increasing fields of study around assessing vulnerability. What you see from the climate models is, an indication, for example, that there will be more heat waves. But the work you just saw about New York City, for example, is an effort to understand who will be most vulnerable to those heat waves. I think that's a growing field of study that could be done in any sector. I also think recognizing that adaptations are designed to reduce vulnerability or to limit the exposure to extreme events, for example, by reducing the amount of critical infrastructure in a floodplain. Those can be better connected, and there's a lot of work in terms of understanding adaptations and technologies that would enable that. And then maybe the final area of study that I think is a growth area is in the contextual implementation of adaptation and other resilience and risk management strategies. So understanding that that adaptation changes have to be in the context of broader social and economic programs and policies, and figuring out how that can be done in a way that minimizes disruption but maximizes resilience and sustainability.
Great. And question 21. why is it necessary for the coupled modeled intercomparison project known as CMIP to add an even lower radiative force scenario such as RCP 1.9? I was working with CMIP 5. RCP 2.6 was the lowest, and the research I checked out mostly focused on RCP 4.5 and 8.5, ignoring the 2.61 because it is less probable to happen. So why should an even lower RCP 1.9 be considered?
So the thing that's important to recognize about these scenarios and pathways is that they are illustrative of the decisions that could be made. RCP 1.9 is an extreme mitigation scenario. There is very strong emissions reductions, and net zero carbon comes very quickly, and then negative emissions beyond that. It's important to recognize this as an option because there are decisions that could be made to push us towards this 1.9 degree world, and those decisions have costs and have benefits. So by including this pathway, we can weigh the costs and the benefits of strong mitigation efforts, and show what it would take to create a high mitigation world along these lines. So what this comes down to, in my opinion, is it's not that we are predicting this pathway. We are showing what it would take should a policymaker ask, how could we achieve a very low global warming level? And in that sense, this pathway is quite useful to understand the complex kind of implementation challenges around those mitigations, but also shows us that some of the long-term effects, even of a high mitigation scenario, for example, on oceans, can still be substantial when it comes to things like sea level rise. So I think the note taker is doing a great job of capturing some of the things I'm trying to say. It's understanding the trade-offs involved in reaching this kind of high mitigation, low emissions future.
Okay, question number 22. Within the modeling of scenarios that have been crossed with vegetation layers, this gives us which types of vegetation which would benefit and others would be at risk. And could these be the cause of fires and pests, among other things?
Thanks for the question. So this is a question I'm going to respond by saying that, to me, this motivates interest and potentially RSET producing further trainings related to specific types of climate impacts. What we were able to present today was the framework by which we approach impact assessment. This question is really asking about the types of vegetation impacts and the competitive balance between different species in an ecosystem. These are important and fascinating questions. Unfortunately, we really didn't cover that today, other than to indicate the types of climate information and the approaches that you might use to answer those questions. I'll just note that this is an important topic because, as we noted, there are more than one type of climate change happening at the same time. And these things can interact not only in the climate system, but also can interact within the affected system itself. So, for example, if we have an increase in drought conditions, that might favor certain types of plants and change the overall kind of array of plants in an ecosystem and the balance of that ecosystem, which in turn can change the vulnerability to fire weather and the fires that may result. These things are being observed all over the world, and the models might give us some foresight and some insight into what might be coming.
Thanks, Dan. Thank you, Alex. And to follow up on what you were just referring to, we did have a series of poll questions in the first part of this webinar series, and there will be a survey sent to you, to everybody that participated in today's training, and as well as last week's, to gauge your interest on what future climate topics that RSIT should be focused on. And we take those very seriously. And so for all of you that are part of this call today and joined last week as well, please do fill out those surveys, because they really guide on what future topics that there's most interest in from the community. So we do encourage you, building off what Alex was just referring to please fill out that survey, and we will base our future trainings focused on climate around your preferences. So do look for that in the coming week. So question 23, does modeling using grids the impacts of climate change in any way counter the biases from climate models?
So I'm not sure I'm following the GPS acronym here, but I think what maybe I'm getting at here is if bias adjustment really can counter the biases from climate models. So I'll at least answer that question. And hope the questioner will forgive me if I've misinterpreted. Bias adjustment is an important aspect, recognizing that climate models tend to have slight deviations in terms of the average temperature or the seasonal progression of rainfall. These are things that are improving with each model iteration, but there will always be a gap between what the model does and the best observational systems. And that is something that we can reduce using bias adjustment, but it is important to recognize that the bias adjustment itself has statistical assumptions. For example, in terms of which variables and which distributions are adjusted. For example, if you are adjusting only the seasonal average temperatures, you will likely miss some of the extreme event characteristics that could happen within that. Or maybe a better way of saying it would be, if you are only adjusting the average amount of rainfall when it does occur, you will not capture changes in the number of rainy days. Those types of assumptions in the bias adjustment must be understood to read into or to draw conclusions from the resulting changes. So there are huge benefits to bias adjustment without a doubt, especially when you factor in mountains and coastlines. And a simple example would be a single 100-kilometer grid cell over a place like Greece will include high mountains and valleys. And if you are growing agricultural commodities in those valleys, your average temperature will be biased by those high mountain peaks. And you will not have a good representation of those valley temperatures unless you have some form of bias adjustment. Those types of effects can change all kinds of things, whether it's agriculture or ecosystems or water resources.
Okay, moving on. Question 24. Do you have examples and/or case studies about the situation in different Latin American and Caribbean countries? In this case, they're trying to look at biomass, for example, sugarcane policy in Brazil and its impact on agriculture and within the Amazon.
So this is I'll answer this question in two ways. The first is from a climate standpoint. The Caribbean is an area with lots of small-scale features that is not very well captured by global models. So the specific climatic zones on Caribbean islands would be better captured by regional models. However, some of the broader patterns of, for example, drought and aridity in the Caribbean can be captured even by global models. Now, the larger question about agricultural commodities and bioenergy crops like biomass, like sugarcane, is again, something that I would love to talk to you from an agricultural impacts perspective. It was not something we presented on today, but there are projections, for example, in that AgMIP project that I've mentioned, that look at sugarcane over Brazil and comparing it against changes in soy and maize in the region. and there are interesting questions related to policies and large-scale market systems in agriculture, which we can explore using not only crop models but agricultural market models. So I'll take this moment to plug one of my own projects, which is this AgMIP project. If you check out agmip.org, that would be a place you might find some connections that are interested in this area.
And question 25, what are some current efforts to get more precise localized data?
There are many. I will say that this includes groups who are setting up local instrumentation. For example, in New York City, we are trying to put more instruments on roofs and throughout the city, so we can understand some of these fine-scale features that are affecting the city. There are also improved satellite products that are getting to higher resolution. There are also many new satellite systems offering finer resolution information via NASA and partners in the private sector even. And this type of information is increasing the overall amount of observations and the resolutions of these. And I would just say that any of these new products is important to ground truth, and having those local instruments still will be quite important. And having that local validation, whether it's in a field or on a rooftop, is always going to be a fundamental part of the scientific process.
Thank you, Alex. Question 26. Is there an interface or portal to incorporate environmental data sets into these broader modeling constructs?
It's an interesting question. There are many efforts to do this. I'm not sure whether there is one single, but certainly there are the bias adjustment community is looking for better data sets to bias adjust towards. The crop modeling community is looking for better information about what agricultural fields are out there and soil conditions, and when people are planting, for example. And some of the recent efforts to harmonize formats of different data sets is proving to be very useful in terms of allowing different environmental data sets to communicate and connect to each other. And the broader effort behind things like CMIP is to create common data sets and formats so that we can harmonize the input conditions and make our models more directly comparable. So maybe just to say again, by having common formats and available environmental data sets, we are better able to drive consistent ensembles of models for our assessments.
Great. And question 27. Since climate models are dependent on different initial conditions, boundary conditions, and ECS, what does this mean for the climate model users?
So I would say that it's important for the climate model users, and hopefully today's RSET training has given you an indication of why these things are important. But just to recognize that the modeling groups themselves are going to give slightly different projections of the future, depending on things like this equilibrium climate sensitivity, ECS. And that those projections will also depend on conditions like the emission scenarios that drive, effectively our boundary conditions coming in, driving the model. The initial conditions are something that is going to affect the first years and maybe decades of a projection, but become less and less important over the future decades because the chaotic nature of the climate system and the broader climate changes start to dominate. So recognizing that each of the initial conditions and the boundary conditions and the model uncertainties, with ECS being just one of several components of what makes a model different. Each of these things affect the long-term projections you might see, and therefore it's important to recognize the use of multiple models and scenarios to understand the future.
Great. Question 28. As climate science is dynamic, how best is existing technology to serve people's adaptation and mitigation measures? Considering the worst case scenario, do we have a robust system to communicate such rapid changes with informed decision making? How about reaching that last mile, for example, Poor Nations SIDS being facilitated in this regard?
So here again, I want to appreciate the question and say it's a very important one. It's not something that we've covered in this RSET training at this point, although it would be a useful topic for future training. And the question, I think, comes from exactly the right perspective, which is that, once we have this information, how can we implement it? How can we turn this into actions? And this does require a implementation framework or set of experts and resources and other things that allow us to create decision systems and be both reactive and proactive. So I've just put a bunch of things on the table here, but the bottom line is taking this climate information to implementation requires planning, requires a recognition of different populations having different needs, and it requires connecting the climate information to the specific actions that are under consideration, whether it's to reduce vulnerability to a drought for an agricultural system, or provide some kind of flood protections for a tropical cyclone.
Great, thank you so much. And let's see, question 29. The climate simulation models often rely on additional models like crop yield. This clearly indicates that the uncertainty thereby increases exponentially with minor errors in any of these models. How do the climate models mitigate these errors?
So we noted in the presentation that the error can increase with additional links in this chain from climate information to impact sectors. Exponentially, I'm not sure I agree with that, because there are different types of error propagation. But the overall concept, I think, that the question is asking is an important one. So what we do is we ask specific questions of each type of model, and we look at how that uncertainty cascades to figure out what important pieces of information are leading to those uncertainties. So another way of saying that is, if we look at a given action, for example, a crop model that is testing an earlier planting date, if the broad variety of climate models and crop models that simulate that give us an uncertainty that is so large that we cannot determine a course of action, then we might try to trace back and say, is it because of the rainfall, or is it because of the crop representation of a certain process, or is it because of the pathway uncertainty in our climate projection? So we can either use that process to identify the key sources of uncertainty, which is useful, or we might find ourselves in a situation where, despite that uncertainty, it is still clear that there would be a benefit to that action. So, for example, if the probability of that adaptation being successful is 80%, regardless of the scenario that we're provided, that might be enough information to motivate that action. And in general, this becomes a longer engagement with stakeholders, where we would ask, to what level of confidence would you need to make an action, and how does that compare to the level of confidence that the climate impact assessment can provide? And there are there are many cases where the information from the model is enough to take some action, recognizing that a lack of action is in its own way a decision as well. So oftentimes what we are trying to do is provide more information and scientific backing or understanding as a foundation for the actions that are being taken.
Well, Alex, thank you so much. We are at the top of the hour, and to be respectful for your time and to Dan's time, and as well as everybody that has joined us for this lengthy 2-hour webinar, before I wrap things up, I just wanted to hand it over to you if you had anything you wanted to say to our participants.
I think for the most part, I'm happy to see such interesting questions, and I see that we still have a large number of attendees listening to these questions. So we will try to answer as many of them as we can and post the results online, so you can see if your question was answered. And in general, please do get in touch if you have specific questions about what we've done. Both the RSET team and myself would be happy to receive some questions. And in particular, please speak out if there is more that you would like to learn about in terms of these RSET trainings. And remember that this part 1, part 2 climate training was meant as an introduction and hopefully a foundation builder for more detailed RSET trainings to come. Thank you very much.
Great, thanks, Alex. And just a reminder to everybody, there is a homework assignment. You can find it from the training website. Do access it. That is live as we speak. So if you wish to get a certificate for attending both parts of this training, as well as to get that certificate, please do go ahead and complete the homework assignment. Thank you, everybody, for joining. This has been a really successful 2-part training. Very, very big thanks to Alex Ruane and Dan Bader from the Goddard Institute for Space Studies. Thank you so much for joining for both parts and contributing so much to this webinar series. I also want to thank everybody from the RSET team. That's Amita Mekta, Brock Blevins, Selwyn Hudson-Odoi, and Jonathan O'Brien. They've been in the background working magic for all of you, even though you might not have been able to see them. Thank you, Selwyn, for transcribing all of the answers as they've been taking place live. We greatly appreciate everybody, and please do fill out the surveys that will be coming to you within the week, because they will help guide us in future training. So thank you for everybody for tuning in, and we look forward to seeing you at our next training. Thank you.